Hello, this is Mr. Ezra, and today we are going to continue our discussion of characteristics of graphs, and particularly graphs of quadratics. So quickly, just to review with you a little bit, we talked in the last video about domain and range. So if I ask you what is the domain and range of this parabola here, this quadratic function, you might remember that domain is x values that are on the function from left to right. Well, we have an arrow on the left and an arrow on the right. So that means that -1 comma something, -2 comma something, -50 million comma something are all on the parabola. And on the right side, we have 3 on the graph, 4 comma something, 5 comma something, and forever to the left. So since we're going forever from the left to forever to the right, we would say that the domain is from -infinity to positive infinity in interval notation. The range is limited with these types of functions. Since this one is open up, the bottom of our range comes from the y value of the vertex. That's going to be -2. So the lowest value is -2. And remember, since -2 is on the function, it is included as part of the range, we use a bracket. And we go bottom to top for range. So since -2 is on the function, all of the y values up forever are included. So we have y value of -1, something comma -1, something comma 0, something comma 1, all the way up to something comma almost infinity. We're approaching infinity as we go up, so we'd use infinity there, and that is our domain and our range. Another thing that we looked at were intervals of increase and decrease. I want to remind you that when we talked about intervals of increase and decrease, we always describe them using x values. What we want to know is from left to right, where is the function increasing and where is it decreasing? So it might be a good idea to start by looking for a point where the function changes direction. So we follow this from left to right. It's decreasing from left to right. So we get to that point, and then it changes direction and it starts to increase. So we've got a decreasing interval on this side and an increasing interval on this side, and right in the middle is where it changes direction. Well, it changes direction at an x value of 1. So forever from the left, that's -infinity, to +1, make that look more like a 1, to +1, this function is decreasing. And then from +1, forever to the right towards infinity, this function is increasing. So if I want to talk about intervals of increase and decrease, the interval, there's only one, of decrease, is going to be from -infinity to 1. And remember, these always get parentheses because when you talk about an interval of increase or decrease, it's not increasing at one spot, right? It has to be from somewhere, it has to be an interval from -infinity to 1, it's increasing, but it's not increasing at just one spot, or decreasing at one spot, I should say. Okay, it starts to increase, so the interval of increase is going to be from 1, where it changes direction and starts to go uphill. And it increases forever to the right, always going up towards infinity. You remember, resist the urge to use y values. You got to think left to right, what's happening. A lot of times, if you kind of break it up, use a highlighter or something to break up your function where it changes direction. Let's change that to. Then you can see that decreases over here and increases. All right, well, that's the old stuff, the stuff we talked about in the last video. Let's move on to some new stuff. So today we want to add a few characteristics. One of those is called an axis of symmetry. And the axis of symmetry is not something that you will see on the graph. You can add it with a dashed line, but it is an invisible line that essentially cuts this type of function in half. It is the line over which the graph would perfectly match if you were to fold it. So if I took my function here and I folded at x equals 2, what's over here would line up perfectly with what's over here. What's here would line up perfectly with what's over here. The left side and right side match up perfectly. The axis of symmetry for a quadratic function is always in the forms of x equals something, right? So the axis of symmetry for this function is going to be x equals 2. It is important that you don't just write 2, because 2 is a number. And we're trying to describe a line. This axis of symmetry is a line, so we need a linear equation, a linear function. And this x equals 2 describes the line where all of the x values are positive 2. All right, that's the axis of symmetry. Easy peasy, lemon squeezy. Another term that you may or may not know, I'm not sure, is extrema. And extrema is basically a fancy-pantsy Mathanese word for maximums and minimums. And at this point, we're going to just talk about maximums as the highest point on the graph and minimums as the lowest point on the graph. So if I have a parabola that looks like this, there's going to be a minimum. The extrema is going to be a minimum. And if I have a parabola that's open down, then the extrema is going to be a maximum. So quadratic functions are either going to have a minimum or a maximum, one or the other. Can't have both. So what would be the extrema in this case? Well, we need to find the highest or lowest point. Okay, so remember, we follow it along. This is called, anybody remember this term? It's called a vertex. So you find the vertex, and the vertex in this case is the extrema. Now, what type of extrema is this? Is it a lowest point or is it a highest point? It's the lowest point. We call that a minimum. The minimum, or the min, is the point 1, comma, negative 2. Okay, type of extrema is minimum. Is there a maximum? This is a question that I get a lot. You know, a lot of students I've asked, what is the maximum here? They will say infinity because there's an arrow going up. But in my opinion, in mathematics, I guess, infinity is not a point, right? If extrema is the highest or lowest point, infinity is not a point, it's a direction. So we can't really use that. So when you have a function like this, there's only one extrema. It's this valley here, in this case, this point where it's the lowest point. There's no highest point because it keeps going up forever. Another thing that you are expected to know and be able to find are called zeros. We also, just to confuse you, call them roots. So zeros, roots, solutions, and intercepts. And more specifically, we're talking about x-intercepts. All right. These terms all mean something slightly different, but we use them interchangeably when we are talking about the point where the graph crosses the x-axis. Okay, on a graph, that's what we're looking for, the point where the graph crosses the x-axis. Okay, these are called zeros because if you plug in the x value, you get an outcome of 0. We call them solutions because it is the solution to the equation if we set the function equal to 0. There's a reason it's called a root. It's called an x-intercept because it crosses the x-axis there. So all of these things are kind of the same thing. Even though their definitions are slightly different, what we really want to know is where does the function cross the x-axis? So what are the solutions here? Well, this crosses the x-axis in 2 places, right here and right here. These are the 2 points where it crosses the x-axis. So the solutions are, and remember, I might ask what are the solutions? But I could have just as easily asked, what are the zeros? Or I could have just as easily asked, what are the roots? Or I could have just as easily asked, what are the x-intercepts? Technically, I'm talking about the same thing for all of those. Now, this point is 1, 2, 3, 0, 3, 0. We also have a solution, or a 0, of 5, 0. I'm not very picky about how you write solutions, zeros, or roots. If you just write it as 3 and 5 as just where it crosses the x-axis, I'm usually going to give you credit for that. So either of those ways to represent the answer would be found as coordinates, or as numbers on the x-axis. Those are the solutions. Again, intercepts are just where the graph, the function, crosses an axis. The x-intercept is where it crosses the x-axis. It's always going to be in the form of some number, 0, just like we saw a second ago. The y-intercept is the point at which the line crosses the y-axis, and it's always going to be in the form of 0, some number. End behavior is something that some students have to get used to. They have to get used to thinking about end behavior in the way that I'm asking you to write in behavior. So essentially we want to know is what a function keeps doing after it leaves the graph, as it continues on forever in some direction, okay? With these types of functions, we're going to say as x approaches infinity, and what this is a description of is this is as x goes to the right. Okay, as x approaches infinity, we want to know what is happening to y. What is happening to f of x? Where does it go? So remember, y and f of x are the same thing. So you could put y here and that would be fine. Right? Where does it go? Is it going up? Is it going down? Is it going towards it? Is it approaching a number? What is it approaching as it goes to the right towards infinity? So this is going to be a fill in the blank kind of a thing where you can always put x approaches infinity. F of x approaches, the arrow means approach, approaches something. And we're going to talk about that in a second through an example. The next thing we want to know is on the left side what's happening. So on the left side, we're going to say as x approaches negative infinity. If we have a coordinate, x going to the right is going towards infinity. X going to the left is going towards negative infinity. So that's what we're saying here. X approaches negative infinity means as we travel along this function to the left. When you write this, you don't have to write the words left or right. Okay, you just write x approaches infinity, x approaches negative infinity. And when we do this, we want to know, well, what's happening to the function? Is it going up? Is it going down? Where is it going? So this is going to be a fill in the blank here, right? As x goes towards negative infinity, what's happening to y? Is it going up, down, somewhere else? So we have two examples of end behavior here. So remember, the nice thing about this is when you get used to writing it, we're going to say as x approaches positive infinity, what's happening to y? And as x approaches negative infinity, what's happening to y? Now, I can't show you this through the computer screen, but a lot of times I'll put my finger on the function. Right? I'm going to put my finger and I'm going to travel along this function. And I'm going to look at what's happening at that end. So remember I said that this is to the right, correct? So as I go to the right, my x values are increasing. What's happening to my y values? Well, they would keep going down, 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 down. And as I keep going down, what am I getting closer and closer to? Negative infinity, right? And on the left side, as x approaches negative infinity, x arrow negative infinity on the left side, put my finger somewhere on the function and I start going left, down, 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 down. And again, I would keep going down forever and ever towards negative infinity. So the way this kind of reads is as we go to the right, we go down. As our function travels to the left, it goes down. Right is down, left is down. That's all there is to it. It's just a kind of a funky way to write it. Okay, we'll do the same thing here. We're going to go ahead and put as x approaches infinity, or as we travel to the right. What's happening to the function? Okay, well, as I travel along this function to the right, it's going up, 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 forever and ever towards, and up goes towards positive infinity. Right? As those y values increase forever, they're going to go towards positive infinity. And as our function goes to the left, as x approaches negative infinity, that's a fancy way for us to say, a mathanese way for us to say left. We're going left, up, 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 and again, we're going up, up, and up goes towards positive infinity, the positive biggest number that you can think of. So f of x would approach, again, positive infinity. So this is essentially fill in the blank, right? The only thing that's going to change with these ways to represent end behavior is we're going to put negative infinity or positive infinity. Now, there's simpler ways to say this. I mean, you could say, as I go right, I go down. As I go left, I go down. But I want you to be kind of specific with the math here. So you don't have to write the words right or left, but I do want everything else there. Same thing over here. You don't have to write right or left, but this is what I should see on your paper when I ask you to describe end behavior. And our last question today, it says analyze this graph, and here we're asked to do a whole bunch of stuff. We want to find domain, we want to find range, we want to find the axis of symmetry. We want to find any extrema. Intervals of increase and decrease. Zeros in behavior. And it's not on this list here, but I'm going to add something, a characteristic we mentioned, y-intercept. When we find the 0, we're going to find the x-intercept. Let's also find the y-intercept. So let's kind of go through this as quick as we can. Domain, remember, arrow left, arrow right. The x values that are on this function travel from negative infinity to positive infinity. These always have to be left to right, least to greatest. Range is bottom to top. So since I have an arrow down, I've got y values from negative infinity up, and I stop getting y values here at 4. It's my highest y value. So I go from negative infinity to positive 4, and since 4 is on the function, this negative 3 comma 4 is a number on the function, then I'm going to use a bracket there. The axis of symmetry is that invisible line that travels down through the function. This is the axis of symmetry right here. Well, it is x equals negative 3. Remember, you have to have the x equals. That's important. You can't just put negative 3. That's a number, not an axis of symmetry. All right, the extrema. Well, I want to communicate that this is what type of extrema. Is it a minimum or a maximum? The highest point here is a maximum. I'm just going to put max there, and the maximum is at the point negative 3 comma 4. Now, let's clean this up just a little bit. I'm going to keep this line here. Maybe I'll change it to be kind of like a green line there. Okay. For increasing and decreasing intervals, I'm going to use x values. So if I'm coming from the left, I'm coming from negative infinity. And then I'm increasing from negative infinity to this point right here. This is where I stop increasing, and that is at negative 3. And I start from that point, I change directions, and I start to decrease. I'm going downhill forever to the right. And remember, forever to the right is along the x-axis towards positive infinity. So increasing would be negative infinity to this x value. Decreasing would be from negative 3 to positive. We have two zeros at negative 5 and negative 1. Put those as coordinates. But remember, you can just put negative 5 and negative 1. You can just put the numbers for zeros. These are also called x-intercepts or roots or solutions. Okay. In behavior, I probably should have given myself a little bit of space, but once you get used to writing, it's not that bad. I'm going to go to the right, and I'm going to go to the left. On the right, down. That's negative infinity. On the left, down. That's also negative infinity. So both right and left are going down towards negative infinity. Okay. And the one thing that I added here is called a y-intercept. It's where the function crosses the y-axis. So that's x, that's y. On the y-axis, it crosses at 0, negative 5. So this is all of the characteristics at this point that I'm going to ask you to learn about. The nice thing about getting good with these characteristics now is that as we move on to other types of functions, so we're going to talk about polynomial functions and rational functions and logarithmic functions and exponential functions this year. Every time we get to a new function, guess what we're going to go back to? We're going to talk about these characteristics of these graphs. So getting a good foundation now is super important. Well, thank you for tuning in. I'll see you in school.